Dear students, today we are going to discuss about periodic properties and their variations, which is a part of the topic periodic classification of elements. We should begin with the term periodicity. What is meant by periodicity? Anything that gets repeated at regular intervals is called as periodicity. Say for example, in a year, seasons are repeated at regular intervals of time. Similarly, in the periodic table, some of the properties get repeated themselves at regular intervals of atomic numbers. The atomic number intervals are 2, 8, 8, 18, 18, 32. These numbers are referred to as magic numbers. The magic associated with these numbers is, at these intervals of atomic numbers, the properties of elements get repeated. This phenomenon is called as periodicity, and the properties that get repeated at these intervals are called as periodic properties. A total of 9 periodic properties have been identified. Atomic radius, also referred to as atomic size. Next periodic property is ionization energy. Ionization energy is also known as ionization potential as well as ionization enthalpy. Next property is electronegativity. In short, it is called as En. Electron affinity, in short called as Ea. Electropositivity, in short called as Ep. Then metallic and non-metallic character, acidic and basic nature of oxides, valency, and last one is diagonal relationship. These 9 properties are called as periodic properties. Out of the 9, the first 8 properties, they regularly change in the period and group, whereas the diagonal relationship property is limited to only the first 2 periods, and it is observed only among elements of 1A, 2A, 3A and 4A groups only. That is why diagonal relationship is a limited property, but remaining 8 are repeated in a regular manner throughout the periodic table. Now we have to see in detail about these periodic properties, how they change along a period, how they change along a group, and what is the reason for such variations. Let us begin with the first property, atomic radius or atomic size. Atomic radius, it is defined as the distance from the center of nucleus to the outermost orbit. Outermost orbit in the sense, wherever the last electron is present in the atom, that will be taken as outermost orbit. So, atomic radius depends on the nuclear charge as well as number of the orbits. As we move from left to right in a period, atomic number increases, but electron will enter into the same orbit. Hence, in a stepwise manner, nuclear force of attraction increases along a period. As a result, atomic radius decreases along a period from left to right. Whereas, as we move from top to bottom in a group, even though atomic number increases, proportionately new shell is added in a consecutive manner. Due to addition of new orbits, the atomic radius continuously increases down the group. However, as it is, atomic radius cannot be calculated for most of the elements, because except inert gases, all other elements are present in the form of molecules only, and the atoms are bound by means of various types of bonds. That is why instead of atomic radius, different terms like van der Waals radius, metallic radius and ionic radius are in use. Van der Waals radius is applicable for inert gas elements. It is taken as half the internuclear distance between two atoms bound by means of van der Waals forces of attraction. As the van der Waals forces of attraction are very weak, this radius value will be the largest and can be generally compared as equivalent to atomic radius. Coming to covalent radius, this is generally applicable for non-metals. In case of non-metals, the atoms are bound with each other by means of covalent bonds. Therefore, half the internuclear distance between two atoms bound by means of covalent bond is called as covalent radius. Covalent radius is 40% less in magnitude compared to van der Waals radius. Metallic radius, as the name suggests, is applicable for metal atoms. In case of metals, the metal atoms are systematically arranged in the form of definite crystal structures. Half the internuclear distance between two metal atoms bound by means of metallic bond in the crystal structure is taken as a metallic radius. The magnitude of metallic radius will lie in between van der Waals radius and covalent radius. Coming to ionic radius, there are two types of ions. One is cation, another one is anion. Cation is positively charged, anion is negatively charged. So, the exact cationic radius or anionic radius cannot be defined, but theoretically we can say cationic radius is always less than that of atomic radius as well as corresponding anionic radius, because in case of cation, number of electrons will be less compared to the number of protons. Hence, the nuclear force of attraction will be more in case of cations, and as a result its radius is always less compared to atomic radius as well as anionic radius. In case of anion, as the number of electrons are more than that of protons present inside the nucleus, the nuclear force of attraction will be reduced and hence slight expansion takes place. Hence, anionic radius is always higher than that of atomic radius as well as cationic radius. In general, in case of isoelectronic species, with increase in the magnitude of positive charge, proportionately cationic radius decreases, and in case of anions, with increase in the magnitude of negative charge, anionic radius proportionately increases. So, this is the first periodic property, atomic radius, types of atomic radius and their variation in the periodic table. Ionization potential, also called as ionization energy as well as ionization enthalpy. It is defined as the amount of energy required for the removal of outermost electron from a neutral gaseous atom. Ionization potential value depends on many factors. One of the factor is atomic radius. Second factor is nuclear charge. Third factor is screening effect, also called as shielding effect. Penetration power and fifth factor is electronic configuration. With increase in atomic radius, nuclear force of attraction decreases and hence ionization potential value also decreases. Therefore, atomic radius and ionization potential, they are inversely proportional to each other. Nuclear charge, it corresponds to the number of protons present inside the nucleus. With increase in the number of protons, nuclear charge increases and hence nuclear force of attraction also increases. Hence, with increase in nuclear charge, ionization potential always increases. Therefore, ionization potential and nuclear charge, they are directly proportional to each other. Coming to screening effect or shielding effect, in an atom comparatively nuclear force of attraction is less on the outermost orbit because the inner orbits present between the nucleus and outermost orbit absorb the nuclear force of attraction. As a result, effective nuclear charge on the outermost orbit and outermost electrons is less. As a result, less energy is sufficient for the removal of electron. That effect is called as screening effect, also called as shielding effect. With increase in the number of inner orbits and inner electrons, magnitude of screening effect or shielding effect increases and proportionately ionization potential value decreases. So, we can say ionization potential is inversely proportional to shielding effect or screening effect. Next factor affecting the IP value is penetration power. Various sublevels like S, P, D and F, even though they are present in the same energy level, the energy required for the removal of electron differs due to their shapes. The energy required for the removal of S electron is always higher compared to P or D or F. The order of penetration is represented like this: S greater than P greater than D greater than F. That means it is always difficult to remove an S electron compared to an F electron. Last factor is electronic configuration. Some of the electronic configurations are considered to be stable in nature. Hence, whenever we come across the such electronic configurations, the IP value suddenly increases. The most stable electronic configurations are octet configuration, next is doublet configuration, next is completely filled configuration. This completely filled configuration comes in two cases, one is D10, another one is P6. Of course, P6 comes in octet itself. Then half filled configuration is also considered to be stable. This half filled comes in two cases, one is D5, another one is P3. And next most stable electronic configuration is known as pseudo octet configuration, which is represented as n-1 D10, n-1 S2 and P6. In this direction, stability value comparatively decreases. So, whenever you come across these electronic configurations, suddenly there will be an increase in the ionization potential value. Coming to the variation of ionization potential in a period and group. In a period, from left to right, ionization potential value increases, and down the group, as atomic radius increases, ionization potential value also decreases. Along a period, the order of variation of IP values is 1A less than 3A less than 2A less than 4A less than 6A less than 5A less than 7A less than 0 group. That means highest IP values will be observed in case of 0 group elements. The sudden jump in the IP values of 2A group elements and 5A group elements is because of their stable electronic configurations. In case of 2A group elements, NS2 configuration is present, which is a doublet configuration. In case of 5th group elements, the general electronic configuration is NS2 NP3, which comes under half-filled type of electronic configuration. That is why their IP values are comparatively higher than the immediate group elements. So, this order has to be remembered while working out problems on this concept, periodic ionization potential, electron affinity. In short, it is represented as EA. It is a quite opposite property to ionization potential. The two can be correlated as EA is equal to minus IP. We can define electron affinity as the amount of energy released during the addition of one electron to the outermost orbit of neutral gaseous atom. Means with increase in atomic radius, electron affinity value decreases. Hence, along a period, the electron affinity value increases and down the group the value decreases. However, among the elements of 5A, 6A and 7A groups, the second element has higher electron affinity than first element. This is because of two smaller atomic radii of the starting elements of these groups. So, in 5th group, phosphorus has a higher electron affinity than nitrogen. In 6th sulfur has a higher electron affinity than oxygen, and in 7th chlorine has a higher electron affinity than fluorine. Even though these elements are more electronegative compared to phosphorus, sulfur and chlorine respectively. Electronegativity. It is defined as the electron attraction capacity of an element in a covalent bond. When the elements with a higher electronegativity value attract shared pair of electrons towards themselves. Therefore, electronegativity can be defined as the ability of an atom to attract shared pair of electron more towards itself in a covalent bond. This electronegativity is calculated in two ways. One is called Mulliken's scale and another one is called Pauling's scale. According to Mulliken, electronegativity is the average of electron affinity and ionization potential. However, if we calculate the electronegativity values by using this relation, in most of the cases the values come out to be wrong. Hence, for calculation of electronegativity value, we make use of Pauling's scale, which is based on bond dissociation energy values. In Pauling's scale, hydrogen is given an electronegativity of 2.1. All other elements capability of attracting the electrons is compared with hydrogen and given specific values. Pauling's scale ranges from 0 to 4. The highest value of 4 is with fluorine. The next highest element has an electronegativity value of 3.5, that is oxygen. Next highest electronegativity value is 3.0. It is associated with two elements, chlorine and nitrogen. All other elements have intermediate values somewhere between 0 to 4. Electronegativity is not defined for 0 group elements as they do not react with other elements under normal conditions. The electronegativity of first year group elements is taken as almost equal to 0. This electronegativity is also dependent on atomic radius and is inversely proportional. Hence, with increase in atomic radius, electronegativity decreases. Coming to the variation, in a period as we move from left to right, electronegativity value increases. As we move down the group, electronegativity value decreases because of increase in atomic radius. Electropositivity. It is quite opposite property to electronegativity. The ability of an atom to lose electrons is expressed in terms of electropositivity. Electropositivity is dependent on atomic radius in this manner. Electropositivity value is directly proportional to atomic radius. Hence, along a period, electropositivity value decreases, and as we move down the group, electropositivity value increases. This electropositivity value is related to metallic character. Any element with a higher electropositivity value will have higher metallic character. Electronegativity is considered as a characteristic feature of nonmetals. With increase in electronegativity value, nonmetallic character increases, whereas with increase in electropositivity, metallic character increases. Metallic and nonmetallic character. Elements with a higher electropositivity value are treated as metals, whereas elements with a higher electronegativity value are treated as nonmetals. Along a period, electronegativity value increases, electropositivity value decreases, whereas down the group, electronegativity decreases and electropositivity increases. Hence, along a period, metallic character decreases and non-metallic character increases. Quite opposite phenomenon takes place in case of groups. Metallic character increases, whereas non-metallic character decreases down the group. The elements with the average electropositivity and average electronegativity values are treated as semi-metals, or these are also called as metalloids. Generally, they will possess 50% ionic character and 50% covalent character. Basic nature of oxides. In general, non-metallic oxides are acidic in nature, while metallic oxides are basic in nature. So, along a period, non-metallic character increases, therefore, acidic nature of oxides also increases. Whereas, in a group, metallic character increases and hence basic nature of oxides increases. So, along a period, basic nature decreases, whereas in case of group, as we move from top to bottom, acidic nature decreases. However, as we move along a period, somewhere in between we come across peculiar compounds which behave both as acids as well as bases. Such substances are called as amphoteric oxides. Amphoteric oxides can react with both acids as well as bases. Aluminium oxide is an example for amphoteric oxide. It is a peculiar case. Aluminium is a metal, but its oxide has got amphoteric nature. That means it can react with both acids as well as bases. The combining capacity of an element with others is defined as valency. In general, valency is defined in three different ways. One is with respect to hydrogen, another one is with respect to oxygen, and another one is with respect to electronic configuration. With respect to hydrogen, valency is defined as the number of hydrogen atoms with which one atom of an element combines to form a stable hydride. Number of hydrogen atoms with which one atom of an element combines to form stable hydride. That number is taken as valency with respect to hydrogen. Say for example, if you look at the elements present in second period, the elements are lithium, beryllium, boron, carbon, nitrogen, oxygen, fluorine. Neon is not considered because it is non-reactive in nature and valency is not defined for zero group elements. When these elements are made to react with hydrogen, lithium gives lithium hydride, beryllium gives beryllium hydride, boron gives diborane, carbon gives methane, nitrogen gives ammonia, oxygen gives water, fluorine gives HF. So, as per the definition, one lithium atom is combining with one hydrogen atom. Therefore, valency of lithium is 1. Beryllium is combining with 2 hydrogens, therefore, its valency is 2. 2 boron atoms are combining with 6 hydrogen atoms, therefore, 1 boron atom is combining with 3 hydrogens and hence valency of boron is 3. Carbon 4, nitrogen 3, oxygen 2, fluorine 1. So, as you look at these values, there is some correlation between the valency value and the corresponding group number. Lithium belongs to 1A group, beryllium belongs to 2A group, boron belongs to 3A, carbon belongs to 4A, nitrogen belongs to 5A, oxygen belongs to 6A, fluorine belongs to 7A. So, group number and valency are correlated. Up to 4th A group, the group number is equal to the valency. But from 4th A group onwards, the valency is gradually decreasing and it can be represented with the general relation 8 minus G, where G is group number of the element. Say for 5th A group elements, 8 minus group number 5 is equal to 3. For 6th A group elements, 8 minus 6 it is 2. For 7th A group elements, it is 8 minus 7, that is 1. So, with respect to hydrogen, as we move from left to right in the periodic table, the valency first increases from 1 to 4 and then decreases to 1. Up to 4th A group, there is no difference between group number and valency, but from 4th A group onwards, the valency value is equal to 8 minus G. Generally, valency with respect to hydrogen is considered as a minimum valency. Valency with respect to oxygen. It is defined as double the number of oxygen atoms with which one atom of an element combines to form a stable oxide. Valency with respect to oxygen is defined as double the number of oxygen atoms with which one atom of an element combines to form a stable oxide. Say, to understand this concept, let us consider elements of third period. The elements present in third period are sodium, magnesium, aluminum, phosphorus, sulfur, chlorine. Sodium, magnesium, aluminum, silicon, phosphorus, sulfur and chlorine. In order to understand the valency with respect to oxygen, let us consider elements present in third period. Sodium, magnesium, aluminum, silicon, phosphorus, sulfur and chlorine. When we treat them with oxygen, the stable oxides formed are Na2O, MgO, Al2O3 aluminum oxide, SiO2 silicon dioxide, P2O5 phosphorus pentoxide, SO3 sulfur trioxide, Cl2O7 chlorine heptoxide. Now, as per the definition, 2 sodium atoms are combining with 1 oxygen. Therefore, 1 sodium atom is combining with half oxygen atom. Double that number, it will become valency with respect to oxygen. So, that value comes out to 1. For magnesium, it comes out to 2. For aluminum, 3. Silicon 4, phosphorus 5, sulfur 6, chlorine 7. Here, if you look at the correlation between the group number and valency, sodium belongs to 1A group, magnesium belongs to 2A group, aluminum belongs to 3A group, silicon belongs to 4A group, phosphorus belongs to 5th A group, sulfur 6th A group, chlorine 7th A group. So, if you correlate the valency with group number and valency are same. As we move from left to right in the periodic table, the valency with respect to oxygen continuously increases from 1 to 7 and it is treated as maximum valency possible for an element and it is equal to group number. Valency with respect to electronic configuration. The total number of electrons present in the outermost shell of an atom is taken as equal to its valency. Say for example, for first year group elements, electronic configuration is NS1. Second year group, it is NS2. For third year group elements, it is NS2, NP1. For fourth year group elements, NS2, NP2. 5A, NS2, NP3, 6A, NS2, NP4, 7A, NS2, NP5. So, as per the definition, in the valency shell of 1A group elements, number of electrons present are 1, in 2A 2, 3A 3, 4, 5, 6 and 7. So, according to this definition, valency is equal to group number. So, numerically valency with respect to electronic configuration is same as valency with respect to oxygen. The valency values change along a period only. In a particular group, valency remains constant. That means, for first year group elements it is always 1, for second year group elements it is always 2, like that. However, exceptional cases have been observed in the groups 3A, 4A and 5A. In these 3 groups, as we move from top to bottom, the bottom element shows valency 2 units less compared to the previous elements. The phenomenon involved is called as inert pair effect. In short, we call it as IPE. Inert pair effect is defined as the reluctance of outermost s electrons to participate in bond formation with the increase in atomic number. As the s electrons do not participate in bond formation, the valency value decreases by 2 units in these 3 groups. However, this phenomenon is limited only for these 3 groups. In the rest of the groups, the valency remains constant for all the elements. Last property is diagonal relationship. It has been observed in second and third periods that diagonally placed elements resemble closely in their properties, both physical as well as chemical. The second period elements can be represented as lithium, beryllium, boron, carbon, nitrogen, oxygen, fluorine, neon. The third period elements can be represented as sodium, magnesium, aluminum, silicon, phosphorus, sulfur, chlorine and argon. These elements belong to 1A, 2A, 3A, 4A, 5A, 6A, 7A and 8A, also called as 0 group. Now, these elements were found to be very much similar in their physical as well as chemical properties. This phenomenon is called as a diagonal relationship. So, as you can see, this diagonal relationship is a very much limited property observed in only 2 periods of the periodic table, second period and third period, that too in only the first 4 groups, that too only 3 pairs of elements exhibit this property. That is why these pairs are called as diagonal pairs. The first pair being lithium and magnesium, second pair being beryllium and aluminum, third pair being boron and silicon. The reason for diagonal relationship is somewhat attributed to polarizing power. If polarizing power is same for 2 elements, then there will be similarity in properties of corresponding elements. Hence, lithium closely resembles with magnesium, beryllium closely resembles with aluminum, boron closely resembles with silicon in their physical and chemical properties. So, that is about periodic properties and their variation. Magnetic behavior of elements. The way elements respond to external magnetic field, the magnetic properties are defined as paramagnetism, ferromagnetism and diamagnetism. When an element is placed in an external magnetic field, if it is not at all attracted towards it, then that property is called as diamagnetism. Whereas, if an element placed in an external magnetic field is strongly attracted towards it, that character is known as ferromagnetism. If weak attraction towards external magnetic field is observed, that is called as paramagnetism. These magnetic behaviors or properties, they are closely related to the electronic configurations and the number of unpaired electrons. In general, if any element carries 1 or 2 unpaired electrons, it will be associated with a paramagnetic character. When the number of electrons exceed 2, more than 2 unpaired electrons, then that element will show ferromagnetic character. If the number of unpaired electrons in any element is equal to 0, then it will show diamagnetic property. The strength of magnetism is expressed in terms of a term called magnetic moment. Magnetic moment is denoted with the symbol mu and is calculated by using this relation square root of n into n plus 2, where n stands for number of unpaired electrons. Now, how to identify the nature of an element given its electronic configuration or atomic number? Say for example, identify the nature of the following elements: neon, scandium, iron. When elements are specified like that, we have to write down their electronic configurations. If you take the first case, neon, its atomic number is 10. and electronic configuration is 1s2, 2s2, 2p6. So, with this configuration, number of unpaired electrons possible are 0. Hence, nature of neon can be called as diamagnetism. Coming to scandium, its atomic number is 21. Its electronic configuration can be represented as argon followed by 4s2, 3d1. That means in the 3d level there is one unpaired electron. So, here n value is 1. When one unpaired electron is present, the type of magnetism associated is, in case of iron, atomic number is 26, electronic configuration is argon followed by 4s2, 3d6. 3d6 means arrangement of electrons will be like this. A d sublevel consists of 5 orbitals. In those 5 orbitals, 6 electrons can be accommodated like this. Therefore, number of unpaired electrons in case of iron are 4. Therefore, it shows ferromagnetism. Ferromagnetic substances, when kept in contact with the permanent magnets for longer durations, they themselves become permanent magnets. That is about the magnetic behavior of elements. IUPAC nomenclature of elements. This method is used for naming of elements with atomic number 100 onwards. Because in case of elements with atomic number 100 onwards, most of them are synthetic in nature, and scientists from different countries claim for the credit of discovery of that element. So, to avoid the controversy, IUPAC has suggested naming of the elements based on their atomic numbers. In this system, 0 is called as nil and the symbol used is small n. 1 is represented as uni and is represented with the symbol small u. 2 is represented with bi, symbol is small b. 3 is represented as tri, symbol is t. 4 is represented as quad, symbol q. 5 is represented with pent, symbol is small p. 6 hex, h. 7 is represented as sept, symbol is s. 8 is represented with oct, symbol is o. 9 is represented with n, symbol is e. Suppose an element's atomic number is 100. How to write the name of this element and how to represent the symbol of this element. In this element with atomic number 100, starting number is 1. So, it should be represented with u, capital U. Next number is 0. So, it is represented with small n. Next number is also 0. So, another n. So, u, n, n will be the symbol of an element with atomic number 100. So, it should be called as unnil, nilium. Name of the element should end with the suffix ium, em. So, meaning of this name is un means it is beginning with 1, nil means next number is 0, another nil means another digit is also 0, and the convention is name of the element should end with the prefix ium, em. Suppose an element's atomic number is 109. What should be its IUPAC name? As the number begins with 1, we should begin with un. 0 means nil, 9 means n, em. So, element with atomic number 109 should be called as unnil, nem. Symbol is capital U, small n, en. Suppose an element's atomic number is 118. it should be called as unoctium, and symbol has to be UO. Suppose an element's atomic number is 120, it should be called as unbinillium. Symbol has to be UBN. So, this method is particularly useful for elements with atomic number 100 onwards. Which of the following orders of ionic radii is correctly represented? The given options are A, H minus greater than H plus greater than H. Second option is Na plus greater than F minus greater than O minus 2. Third option, F minus greater than O minus 2 greater than Na plus. D, Al plus 3 greater than Mg plus 2 greater than N minus 3. This question is based on the ionic radii. Order is not exactly correct. Why? Because in case of hydrogen, there is only electron present in the first orbit. Therefore, this order is not exactly correct. In case of second one, cation's radius is given as larger than that of anions. Hence, that option is also wrong. In case of C, F minus greater than O minus 2 greater than Na plus. This option is also wrong. A oxide ion is larger than fluoride ion. In D, cation with a higher positive charge is given larger size, which is not possible. So, for this question, there is no correct option in fact. Identify the wrong statement in the following. The given options are, first one, amongst isoelectronic species, smaller the positive charge on the cation, smaller is the ionic radius. Then second option B is, amongst isoelectronic species, greater the negative charge on the anion, larger is the ionic radius. C, atomic radius of the elements increases as one moves down the first group of the periodic table. Then last option D is, atomic radius of the elements decreases as one moves across from left to right in the second period of the periodic table. So, out of the 4 statements given, we have to identify the wrong statement. If we look at the first option, amongst isoelectronic species, smaller the positive charge on the cation, smaller is the ionic radius. This statement is the wrong statement. Why? Because smaller the positive charge, larger the ionic radius. With increase in the magnitude of positive charge, size proportionately decreases. Therefore, the option A is wrong and hence is the correct option for the given question. The correct order of the decreasing ionic radii among the following isoelectronic species is, first option, Ca plus 2 greater than K plus greater than S minus 2 greater than Cl minus. Second option, Cl minus greater than S minus 2 greater than Ca plus 2 greater than K plus. C, third option, S minus 2 greater than Cl minus greater than K plus greater than Ca plus 2. Fourth option, K plus greater than Ca plus 2 greater than Cl minus greater than S minus 2. This question is based on the ionic radii. Concept is, cations with a larger magnitude of positive charge will have the lower ionic radius, whereas anions with a higher magnitude of negative charge will have higher ionic radius. So, applying that concept, we can take the third option as the correct option. Third option as the correct option, S minus 2 greater than Cl minus greater than K plus greater than Ca plus 2. Which of the following represents the correct order of increasing electron gain enthalpy with a negative sign for the elements oxygen, sulfur, fluorine and chlorine? The correct option is B, oxygen less than sulfur less than fluorine less than chlorine. Among the elements with the following electronic configurations, which one may have the highest ionization energy? The given options are A. Neon followed by 3s2 3p3, B. Neon followed by 3s2 3p2, C. Argon followed by 3d10 4s2 4p3, D. Neon followed by 3s2 3p1. The correct option is A, because it has stable half-filled configuration. Moreover, the atomic size is also less in the given 4 options. In fact, this element is from 3rd, 5th A group and element is phosphorus. Next question, which one of the following elements with outer orbital configurations may exhibit the largest number of oxidation states? Given options are A. 3d3 4s2, B. 3d5 4s1, C. 3d5 4s2, D. 3d2 4s2. So, here the given options are the electronic configurations of d block elements. For d block elements, oxidation state is due to the loss of outermost s electrons as well as the penultimate d electrons. Hence, the correct option is C. Here a total of 7 electrons can be lost. Therefore, largest number of oxidation states can be observed in the case of C. Next question, the correct order of decreasing second ionization enthalpy of the elements mentioned are thallium, vanadium, chromium and manganese is. Here the ionization potential value is dependent on electronic configurations. So, the correct option is Cr greater than Mn greater than vanadium greater than titanium. Next question, which of the following electronic configuration of an atom has the lowest ionization enthalpy? Electronic configurations specified are A. 1s2 2s2 2p5, B. 1s2 2s2 2p3, C. 1s2 2s2 2p5 3s1, D. 1s2 2s2 2p6. Lowest ionization enthalpy or lowest ionization energy is associated with the first A group elements. Among the given options, C represents electronic configuration of 1A group element. In fact, the element with this configuration is sodium. So, C is the correct option for the given question. Identify the correct order of the size of the following. Given options are A. Ca plus 2 less than K plus less than Ar less than S minus 2 less than Cl minus, B. Ca plus 2 less than K plus less than argon less than Cl minus less than S minus 2. Third option, argon less than Ca plus 2 less than K plus less than Cl minus less than S minus 2. D. Ca plus 2 less than argon less than potassium less than Cl minus less than S minus. This question is based on the concept of ionic radii and comparison of ionic radii with atomic radii. The general statement is, with increase in the magnitude of positive charge, size of the cation decreases and size of cation is always smaller than that of neutral atom as well as anionic radius. And in case of anions, with increase in the magnitude of negative charge, the anionic radius always increases. So, applying that concept, the correct option here is B. Ca plus 2 is the smallest one, then comes K plus, next argon followed by Cl minus and S minus 2. The correct option is B. Pauling's electronegativity values for elements are useful in predicting. Given options are polarity of molecules, second option position in the EMF series, electromotive force series, C is coordination numbers and D is dipole moments. Pauling's electronegativity scale is used for the calculation of polarity of the molecules. The relation used is XA minus XB if it is equal to 1.7, percentage of ionic character is 50% and remaining 50% will be covalent. So, by using this relation we can identify polarity of the molecules. So, correct option is A, polarity of molecules.